Hey, so we're back. In this video, we're going to be taking a look at some exponential applications. Definitely has a lot of uses and purposes, particularly if you put money in an account and you want to know how much it grows. It can grow annually, monthly, daily, things like that. So we're going to be taking a look at some of those type problems in this particular video. So we already know how to tell the difference between growth and decay. If our base is bigger than 1, it's going to be growth. And if our base is between 0 and 1, it's going to be decay. So these two that are boxed in, you may want to pause and go ahead and copy these two formulas down. If you notice, they're 99.9% the same. The only difference is one of them says 1 plus R, and the other one says 1 minus R. So this is going to be our formula that we're using as we go through and do some problems, and they tell us to put money in an account and watch it grow or decrease or things like that. So the A in the formula is going to be our initial amount, whatever we started with. R is going to be our rate as a decimal. And then this is going to be our time period in years. So again, whatever the problem says we started with, that's going to be the first number. This is your rate as a decimal. And then this is my time period in years. So the only thing that we'll have to differentiate between is if we're going to grow or if we're going to decay. But that will depend greatly on the problem that we're working with. So again, these are the two formulas that we need. You may need to pause the video so that you have these two formulas. And now we're about to go through and try some problems with them. So here is the first problem. The population of the United States was 248,718,301 in 1990 and was projected to grow at a rate of about 8% per decade. Predict the population for the years 2015 and 2025. So we're going to go through and we're going to solve this problem. So first thing we need to recognize is if it's growth or decay. Because the problem gives me a key word, it says grow, then this problem is going to be a growth problem. So we're going to write our formula down. So this is our formula that we write down. And we're going to go through and we're going to plug in our numbers where they go. So A is our initial amount. So that's going to be this really big population number that we have right here. So that's going to go in. So 248,718,301. That's our A that we're starting with. It says to do 1 plus R. So 1 plus 8%. We need to change that to a decimal. So that's going to be 0.08. You move your decimal 2 to the left. The decimal point is right here after the 8. Move it 1 spot, move it 2 spots. So that'll be 0.08. Now, this problem started in 1990, and we got to do 2 years. It wants to know what's happening in 2015 and what's happening in 2025. So we started in 1990. From 1990 to 2015, that is 25 years. So my time period is 25. We're going to go through and do the same thing for the next problem because we got to do 2 years. We're still doing 1 plus. My percentage is still 8%, so change that to a decimal. This time we started in 1990 and we're going to 2025. So from 1990 to 2025, that is 35 years. So 35 is going to be the exponent. Now these are the numbers that we would type into Desmos or some sort of calculator to definitely help us out. So these are the two things that we'll type in. So I've already typed those into Desmos. So let's see what Desmos has for us. And they're going to be extremely large numbers. They're going to be very, very big numbers. So that would be the first two ones that I did right here over here at Desmos. So this is the one after 25 years. So this is the one in 2025. And then this is the one in, the first one is the one in 2015. And the second one is the one in 2025. So the first one was 25 years later, and the second one was 35 years later. So we typed those in. Now, if you look at this, these numbers are so big that Desmos had to put it in scientific notation. So that means that I would take the 17033 and I would add 9 zeros afterwards. Same thing down here. It gave me 3.677, but I got to multiply that by 10 to the 9. So we're going to be adding 9 zeros at the end. So the numbers are so big, past the billions and the jillions, past that. It's a really big number. But these are the correct answers because we typed them in Desmos. So for the first one, I'm going to say 1.7 times 10 to the 9th. And for the second one, I'm going to say 3.67 times 10 to the 9th. So again, these numbers are in scientific notation, so just a shorthand to help us with the problem. The numbers are so big that Desmos had to put it in scientific notation. But nothing's wrong as long as you typed it in correctly. It's just sometimes the numbers are so big, calculators have to shorten it for us, so they put it in scientific notation. Okay, let's try another one. So the next one coming up, Taylor bought a car. So let me zoom out so we can see everything. Okay, here we go. Taylor bought a car for $16,275 in 2011. It depreciates at a rate of 4.25% a year. How much is the car worth in 2019? And in what year is the car worth about $11,000? So the key word in this problem is depreciates. So depreciates is the key word. If something depreciates, it's going to go down in value. So the formula that we need for this is the one that had the subtraction sign. So keywords that you need to look for: depreciate means to go down, appreciate goes up, increasing goes up, decreasing goes down. So you're just reading through the problem, and there should be some keyword in there that lets you know to use the first formula that was 1 plus R, or the second formula that's 1 minus R. But this one's 1 minus, so let's make sure we substitute our numbers in. 16,275 is what we're starting with. 1 minus is 4.25%. We need to change that to a decimal. So you need to change your percentage to just a decimal. So the decimal point was right here after the 4. Move it once, move it twice. So it would be 0.0425. We started in the year 2011 and we go to 2019. So 2011 to 2019, that is 8 years later. And we type all this in Desmos. And we should get, so we're done with this one, done with this one. So we should get $11,498.24. So $11,498.24. So again, once you set up your answer, once you have your formula, you just set it up in Desmos. So my pen won't let me write here, but that is a 2. So $11,498.24. So type your whole expression in Desmos or some sort of calculator and it'll give you your answer. So what happens with this car is that it's depreciating. When something depreciates, it goes down in value. When something depreciates, it goes down. So she bought it for this amount, and then now it's this amount 8 years later. All right, the last formula that we need to write down. So far our interest has only been growing yearly. So 8 years later, 25 years later, and it's only been happening once per year. But we also can compound things annually, monthly, quarterly, daily. So we can make our money turn over multiple times. So that is called compound interest. So, compound interest formula. The total amount of an investment A earning compound interest is the following. So, this is the formula that you need to make sure you jot down. Where P is the principal, R is the annual interest rate, N is the number of times the interest rate is compounded per year, and T is the time in years. So, we're going to go through, and this time our money is going to compound quarterly, monthly, daily, semi-annually, and things like that. And we'll talk about what those numbers mean. So P is still what we're starting with. It's whatever we're starting with. 1 is still the same. Plus, all of these are going to be plus because, like, if you put money in an account, you want it to grow and things like that. This is still going to be my rate as a decimal. So R is still the rate as a decimal. N is how many times it's happening per year. And then T is my time period in years. So similar to the other formula, except for the other formula, I was only doing it once a year. Now I can do it 12 times a year or 4 times a year, things like that. So we're going to go through and we're going to do a couple problems with this formula so that you'll know what number to put in for your N values. So here's the problem that we're going to work on. We're going to find the final amount of a $100 investment after 10 years at 5% interest compounded annually, quarterly, monthly, and daily. So the key word in this problem, like how you know to use this formula, you use this formula if it says compounded. So that's the key word. If it doesn't say compounded, then use the other formula that I just showed you, the A equals P1 plus R to the T power, use that one. But if it says compounded, then we're going to use this one right here. All right, so here we go. We're going to go through and we're going to start with annually. And we're still using this formula up here. I'm going to switch pens because my blue pen is dying there. So we're going to still going to be using this formula. P is going to be the number that we put into the account. That's $100. 1 plus, we need to change our percentage to a decimal. So this is 5%. So in decimal form is 0.05. N is how many times you're doing it. So the first one is like a 4-part question here. The first one says annually. Annually is 1. And then on the outside, it says N times T. N is how many times it's happening per year. So that's just a 1 because annual means 1. And your time period in years. So we're talking 10 years later. So 10. Okay. So 100 times parentheses 1 plus 0.05 divided by 1, close parentheses 1 times 10. And we type all that in decimals, which I have already. And ta-da, we got $162.89. $162.89. All right, let's try the next one. So that's annually. Now we're going to take a look at quarterly. So this one is going to be quarterly. Same thing. We're still going to be on whatever we start with. So we start with 100. That's going to go in 100. 1 plus. R is still our rate. We're still working with the same problem. So we're going to change that to 0.05. N is how many times it's happening per year. Since I'm doing quarterly, the number quarterly means 4. So quarterly. And now it says your exponent is N times T. So N is 4. And we're still doing 10 years later. So I got all these numbers from the problem. It's just a matter of making sure we substitute those into the correct spot. Now over here in decimals, all I got to do is change my N value. Now N is 4 because quarterly, and then this is 4. So now we have $164.36 after 10 years. All right, 2 more. So we did annually, we did annually and quarterly. Now we're about to take a look at monthly. Everything is going to be the same. I still put in $100. I'm still changing my percentage. Monthly is the number 12. So when I come over here and type this into decimals, the only thing I need to do is to change the 4 to a 12 because I'm doing it monthly. So monthly is 12. There's 12 months in a year. Now we have $164.70. So 164.70. And last but not least, it asks us to do it daily. So last but not least, we're going to do it daily. We put in $100. My percentage is still the same, but you have to change it to a decimal. Now, daily is 365 because we're doing it every day, and there's 365 days in a year. So over here in decimals, we'll change it from monthly to daily. And now we have $164.87. So 164.87. So you know to use this formula. Let me zoom out a little bit here. You know to use this formula if it says compounded. So the key word with this is the word compound. If you are